All right, so welcome to lecture on chapter 13, 1 and 2. Before we get going on that, I want to show you guys some stuff I put up on Canvas. So I'll show you a little bit about this today, some websites you can use to help you visualize some of these ideas. So there's a couple. I really like GeoGebra. That's what we'll take a look at today. And it'll help you to visualize some of these things in 3D that we're going to be talking about. I think actually maybe Dom showed you a little bit about this last week too, but here's just some information that I posted here. And then in addition, I posted some review notes for the midterm. So remember, June 1st through 5th is an exam for both 230 and 231. It's going to cover all of chapter 12 and then 13, 1 through 4, which we'll be doing in lecture today and tomorrow. And so anyway, here's some review notes that you could take a look at. And then also, I have this sample exam solutions page. And so both the 230 and 231 websites have some sample exams that you can look at. So you're going to want to look at the first exam for 230 and then the midterm for 231. They cover the exact same material that our exam this weekend is going to cover. And so it has the exams there and some of the solutions, but for the ones that don't have the solutions there, I've posted here. And then in addition, there's a 231 website that has all their midterms and the solutions aren't there, but I posted them here. So make sure you take a look at that stuff. And then as far as the exam goes, remember it's going to be through Examity. Hopefully everybody's all set up with their account. They've done the technology check, and hopefully you've scheduled it as well. I think in the message I sent out yesterday, I reminded you that when you first set up your Examity account, it asks you for your local time zone. And from there, it sort of translates everything to there. So if you're in State College time zone, the exam opens at midnight on June 1st and closes at 11:59 p.m. on June 5th. But if you're in a different time zone, you're not going to see those exact hours, but it should all be relative to your local time zone. And just triple check, make sure you show up at the time that you've scheduled. If you're concerned about something going wrong, maybe schedule it for either the first or the second so that if something goes wrong, you can take it on either the third, fourth, or fifth. If you do have to make an emergency schedule on the day of, I think there's a small fee, like $5 or something like that. But otherwise, it's included in your tuition. But yeah, just thought I'd point out some of that stuff. I guess we can get into the actual lecture now. So let me stop sharing that. Share these slides. All right, so let me see, I can get the chat, okay. All righty, so chapter 13 is talking about curves for the entire chapter. And so today we'll sort of do an introduction to curves, the way that we'll talk about them. And then tomorrow we'll do some more in-depth calculations regarding them. And so it turns out that for our curves, we're going to represent our curves using vector functions or parametric equations, which are basically the same thing. And so if you think back to what we did last week, if you ask yourself, what's the simplest kind of curve? Well, the simplest kind of curve is a line. And so we talked about line equations in section 12.5. And basically, our curve equations are going to be an extension of those ideas, that the equations are going to be a little bit more complicated, but structurally, they're the same as the line equation. And so, yeah, if you recall what we talked about last week, we set up a line equation by, we had a point and we had a direction vector. So we initially set up the vector form by writing the position vector of a point on the line, and then we did plus t times the direction for that line. And so then if you do the vector arithmetic, that's how you get this form right here. And so yeah, basically these component functions for our line are just linear functions, right? As far as t is concerned, x naught plus at, x naught is some number, a is some number, so t is our variable, and that's how our line equations worked. And so to trace out a curve, we're just going to have slightly more general component functions. So instead of linear functions in each of the three components, you can have any functions, f of t, g of t, h of t. And so instead of tracing out a straight line like they would have before, that you get position vectors of different lines, different points on the line, instead of tracing out a straight line, you're going to get position vectors of points on a curve. And so again, position vectors is that one time in this course where it's a little confusing. Am I talking about a point or am I talking about a vector? A position vector, we'll always call R, starts at the origin. And so it starts at the origin, and if its components are f, g, h, it's going to point to the point whose coordinates are f, g, h. So we'll usually write it in vector form, but the whole idea is to think of, this vector equation is giving you the x, y, and z coordinates of points that live on our curve. Okay, and so you talked a little bit about this kind of stuff at the end of Math 141. I think one of the last couple topics you did was parametric equations. And so just sort of a brief review to maybe bring back your, refresh your memory on this, and we'll do some examples today. But for example, if you have a curve in the xy plane where y is a function of x, that's sort of our most common way of talking about a curve in the xy plane, is y equals f of x. And so if you wanted to get parametric equations for that, or a vector equation to trace that out, the idea is that once you know x, this equation here tells you what y has to be, that knowing x tells you what y is. And so you could be lazy and let x be as simple as you want in terms of t. You could just say, you know what, let's let x be t, and therefore y is going to be f of t. And so that is one way you could do that. So I guess it doesn't have to go this way, but one way you could do it is r of t is, t comma f of t will trace out your y equals f of x curve. If you wanted to instead deal with x in terms of y, so the main difference is, remember, functions, you have this vertical line test that each input can have only one output. So if y is a function of x, you have to pass the vertical line test. And so let's say you have a curve that doesn't pass the vertical line test. Maybe it looks something like this. And in that case, if it passes the horizontal line test, if each y value only gives you one x value, then you could express x as a function of y. In which case now you're really just interchanging the roles of x and y. It's not a huge deal. If you could just let y be t, and then x would be g of t. And then if you think about a circle of radius r, let's say, centered at the origin, let's try to draw that a little bit better. So the issue with the circle is that it fails both the horizontal line test and the vertical line test. So if you wanted to do y in terms of x, if you go to solve for y in this equation, you'd get that y is plus or minus the square root of r squared minus x squared. And so it's true that, yeah, you could let x function as your parameter, but you'd have to have like two pieces. You could do like r of t, r1 of t is t comma square root r squared minus t squared, but then your other piece would be r2 of t is t comma minus square root of r squared minus t squared. So that to trace the entire circle, you'd have to do it in two halves. And instead of doing that, I think it's best to let cosides and sines do the work for you. So the best way to trace out an entire circle is to let x be r cosine t and y to be r sine t. And so those three tricks will be good if you're starting with a curve that you know and you're trying to figure out a vector equation for it. And then also the same kind of skills are helpful if you're given a vector equation and you're trying to figure out what the curve actually looks like. And so the other thing you could do is something called eliminating the parameter. And so that's sort of what that means is you get rid of t and find a relationship between x and y. So let's do a quick example of that, and then we'll come back to this slide to talk about this idea of projections. So, okay, let's say I have the curve r of t is cosine squared t, comma, cosine t. And so at the end of the day, just think all this is it's giving you x and y each in terms of t. You can think of t as time, and this equation gives the position of a particle at time t. And so as you plug in different values of t, you're tracing out the trajectory that a particle takes. So if you have a vector equation like this and you want to figure out what the curve looks like, something you could do is just pick some values of t and plug it in to get different values of x and y. So when t is 0, cosine of 0 is 1, so I'm at the point 1, 1. And so you can draw that t equals 0, we're at the point 1, 1. When t is pi over 2, for example, cosine t is 0. So at t equals pi over 2, I'm at the point 0, 0. When t is pi, cosine of pi is -1, but then cosine squared of pi is +1. So we're at the point 1, -1, which I guess is here. So t equals pi, we're at 1, -1. Okay, and then like at 3 pi over 2, cosine is 0 again. So we're at the origin again. So I guess what's happening is our particle sort of goes this direction for 0 to pi over 2, and then when t equals pi, it's here, but then it turns around, and at t equals 3 pi over 2, it's back at the origin, and then at t equals 2 pi, cosine of 2 pi is 1, we're back at 1, 1. And so I guess it turns around, it traces out that same path, and then, okay, cosine t we know is 2 pi periodic, so that's just going to keep on going forever. So it's going to keep on going back and forth. And so that's one thing you could do if you're given a vector equation, just plug in some values of t and see what it is. But we can also do what I alluded to up here, eliminate the parameter. So if you have a really complicated set of equations, this isn't really something that's going to be all that useful. But when you look at this example, cosine squared t, comma, cosine t, you start to realize that, yeah, notice that it's saying that y is cosine t, because that's at the end of the day, you want to think of the components as the x and y coordinates of points on your curve. So if y is cosine t, and x is cosine squared t, well, cosine t is y. So essentially what I've found is I've found that x is y squared. And so that's what I mean by eliminating the parameter, that I've gotten rid of t, and I've found a relationship between x and y that helps me make sense of this. And so now, okay, that tells us that this curve is part of the parabola x equals y squared. And then if you look at y is cosine t. What's the range of cosine t? It's -1 to 1. So it's not the entire parabola, but instead it's just the part of this parabola for y between -1 and 1. And so, yeah, you're going like this, and then you're going back, and then back and back. It just keeps repeating itself. And so sometimes you could get the entire thing. So for example, let's go over here. If I had r of t is t squared comma t, then that would be the entire parabola x equals y squared, because the range of t is everything. If I plug in all values of t, I get all values of y, and so I get that entire parabola. Whereas if I did something like r of t is t comma square root t, then that's going to be like the y bigger than or equal to 0 half of the parabola x equals y squared. Because if you think the square root of t, that is always giving us the non-negative square root. And so this ties back to what I mentioned in recitation on Wednesday of last week, so recitation 1 of week 2, that you can have different parametric equations that give you the same line. That's what I mentioned last week, but now we're just talking about curves. It's the same deal, that there are different equations that can give you the same curve. For example, if I had, I could also restrict my domain and say r of t is t squared comma t for t between -1 and 1. That's really the same exact thing as doing cosine squared t comma cosine t. That there's different ways you could describe the same curve. But that based on the range of various pieces, you might restrict yourself to, you might get more of it, you might only get half of it, you might get way less than half of it. And so that's something you have to be on the lookout. And so it should make intuitive sense that, remember, we're thinking about this as the position of a particle at time t. And so if you have two cars driving on the highway, you know, one car traces out this curve, the path that it takes on the highway. And then let's say you have another car behind it that speeds up, slows down, speeds up, slows down. So those are going to be two different vector equations, right? They're not at the same place at the same time, so they're different equations, but they're tracing out the same road. And so that's one way you can think about all this. Okay, and then going back to this slide, something we could do, so far we've just been focusing on the XY plane situation, which is a little bit simpler, obviously, compared to X, Y, and Z space. So if you're dealing with space, then what you could do is you can look at two variables at a time and essentially consider what the shadow of this curve would be and try to make sense of it that way. So what do I mean by that? Okay, so let's say I have this curve cosine t, t sine t. So if you're really stuck, you know, one way you could do it is pick some values of t to get x, y, and z coordinates, and then just draw those. That's what the GeoGebra website is going to do when I show you this in a second. That at the end of the day, this is just giving us x, y, and z in terms of t. So pick some values of t, plug it in, connect the dots, and that's all that's really happening. But instead, let's try and see if we could get a better idea of what's going on here. And so the idea is we could think about projections or shadows into the coordinate planes. So for example, the XY shadow, I'm just going to look at X and Y. So like for XY shadow, I'm just going to think about what X equals cosine T, Y equals T looks like. So for the XY shadow, you're just forgetting about Z. So remember, these components you want to think of as X, Y, and Z, each in terms of T. Okay, and then cosine T comma T, you could either think about this as eliminating the parameter, or you can recognize that this is one of our shortcuts, that like, if I notice that y is t and x is something in terms of t, then I know that x is something in terms of y. So x equals cosine y is what we're dealing with here. And so let's think about what that looks like. Well, it looks kind of like y equals cosine x, but it's flipped over the line y equals x because we've interchanged the roles of x and y. So yeah, x equals cosine y is going to look something like that. Okay. And so then the xz shadow is going to be x equals cosine t, z equals sine t. And so then this is another one of our shortcuts. That's a circle, right? Cosine t, sine t, because you could use the Pythagorean theorem to see that x squared plus y squared equals 1, right? Because cosine squared plus sine squared equals 1. And so if we have that, the xz shadow is just a circle. And then the yz shadow is y equals t, z equals sine t. So z is sine of y, which means that when we draw it, z is sine y is going to look something like this, right? That's what sine looks like. And so what this has done is given us different perspectives of our curve. And so it turns out that this is going to be a helix around the y-axis. So let me see if I could draw this. Let's say x is here, z is here, and that's y. It's going to look something like that. That this point here, you know, at t equals 0, you could plug everything in and get the point 1, 0, 0. When you go all the way around here, when t is 2 pi, if you go back up and look at the equations, you'd have the point 1, 2 pi, 0, and so on and so forth. So let's take a look at GeoGebra just for fun to see this. So I think I have to stop sharing on here. For it to let me share here. All right, so, okay, GeoGebra, let's load, please. GeoGebra. 3D calculator. Okay. What let me get there from Canvas? I'm blaming Penn State's internet. Okay, here we go. Okay, so the reason I like GeoGebra, I mean, obviously there's lots of other ways you can use a computer to help you see these things. For example, there's Mathematica, there's MATLAB, there's all kinds of fun things like that that are a little bit more advanced and more powerful, but you have to know some syntax in order to do it. I really like GeoGebra because you don't really have to know what you're doing at all, as I will demonstrate now. So to type in a vector equation, all you really have to do is put it in parentheses. So we had cosine t, comma sine, comma t, comma sine t. And that's like all you have to type in, and you hit enter. It'll add some more stuff here, and if you want, you can adjust the range of t. So it added all this fun stuff here, so I could do like minus 2 pi to, let's say, 6 pi, hit enter. Okay, and then what you could do with your mouse then is just move your perspective around. So what the projections we're doing is essentially telling us what this curve looks like when we adjust our perspective accordingly. So the first one we looked at, remember, was the XY plane. So the colors here, it goes RGB. So red is X, green is Y, blue is Z. So if I look at the XY plane like this, remember we had X equals cosine Y a few minutes ago. And that's what we came up with. And then when we looked at the XZ shadows, so XZ, I want to see red and blue axes, and I saw a circle. So what do you know? There we go. And then the YZ, I want to see green and blue. I had Z equals sine of Y. And there we go. So we're not going to obviously make you draw these, right? We're not making you write out anything by hand for this course. But I think it's good to play around with this. So I really recommend messing around with GeoGebra when you're working on the WebAssign for this week. You won't have GeoGebra obviously for the exam, but it can help you get a feel for these kinds of things. And so obviously if the equations are super duper complicated, you might not gain much from even looking at these shadows, but I think this shadow idea will just get you comfortable with how adjusting your perspective can change what your curve looks like. And so if your equations are somewhat simple, like they are in this example, you can understand that something like this helix, it's sort of spinning around. That kind of looks the way I drew it on the other page. This helix, when you look at it in this perspective, you sort of have a sinusoidal type graph, whereas if you rotate the helix, it's sort of doing something like that. So that's something you can mess around with. So stop share. Let's go back to our slides. Okay, so anyway, I think I even made it on these slides that once I upload them, this will be a hyperlink that'll take you directly there. So that'll be fun. Okay, and then the main idea from 13.1 that we're going to expect you guys to be able to do is come up with equations for curves of intersection of two surfaces. So often in this course, we're going to have two different surfaces, and we want to talk about the points that those surfaces have in common. And it turns out to do any sort of calculation on these curves, we're going to need R of t. Remember, because that's what R of t is x, y, and z, each in terms of t. So y of x of t, y of t, z of t is what R of t is. And so between the calculations we'll talk about tomorrow and for Math 230 in Chapter 16, we're going to do things like tangent lines. Well, actually, we'll do that one today. But then tomorrow we'll do arc length, curvature, coordinate systems. In Math 230, towards the end of the course, we'll talk about the mass of a wire and work done by a force on a non-straight line path and all kinds of fun stuff. And in order to do any kind of curve calculation, we have to have R of t. And so that's the main skill we're going to practice right now is, let's say you have the curve being described to you in a different fashion. How do you get R of t? And essentially, it's just kind of messing around with these nice cases that we talked about here. So let's take a look and practice a few. If you understand these, then you'll be pretty much set for the homework and pretty much set for the exam. So we want to find the curve of intersection of the plane and the parabolic cylinder. Okay, so obviously something like this, well, maybe not obviously, but I'll just tell you, if we had really super complicated surfaces, the equations could be so messy that it's impossible to mess around with them. But the examples we'll expect you to handle are going to be doable. And so the idea here is that we want to mess around with this and keep our ultimate goal in mind, is to get x, y, and z each in terms of t. Because again, we started our discussion on the very first day of class that when you have an equation, that's a surface. So for example, y equals 2z squared, I notice x is missing, and so it ends up being, how's this going to look? I end up getting like a parabolic cylinder. It's going to look something like that. So I should erase this. I should have this go like that. That all the x cross sections are the parabola y equals 2z squared, which is going to look something like that, right? So all the cross sections are going to look like that. So an xyz equation gives you a surface. An xyz equation gives you a surface. So this, of course, we recognize as the equation of a plane. And then the whole idea is we want the curve that these two surfaces have in common. So which points live on both of these things. And so again, yeah, our goal is to get x, y, and z each in terms of t. And so if you look at this, let's say I know what z is. If I know what z is, then I know what y is. So if I know z of t, the parabolic cylinder tells me what y is in terms of t. But then if I look at this stuff, the plane, at that stage, if I know what z of t and y of t are, then the plane equation is going to give me x of t. So as soon as we decide what we want to make z of t, we're basically done. So like, let's let z be t. Because remember, there's infinitely many different correct answers we could do for this. But if we let z be t, that's going to be sort of the simplest one. So then if z is t, y has to be 2t squared in order for this to live on the parabolic cylinder. And then finally, the plane equation tells me what x is. X is 4 minus 2y minus 3z. Again, this is our goal. We want x, y, and z each in terms of t. And so once we've decided what z is, we're done. And so I think now will be a fun time to mess around in GeoGebra. So stop this. Okay, share GeoGebra. I'm just going to refresh this. Start from scratch. Okay, so yeah, let's draw all these things. So for the surface equations, you just have to type in the equation. So y equals 2z squared. That's all I have to type. Boom. And there's our, so it's good for playing around with surfaces too. Remember, we had that since x is missing, all of the x equals 1, x equals 2, x equals 3 cross sections are the same parabola. So if you stack them all together, you get this parabolic cylinder. Guess I did a decent job drawing it. Maybe not that decent, but semi-acceptable. Okay, and then we have our plane, which was x plus 2y plus 3z equals 4. So that's our plane. So essentially we're looking for the points. So that's cool. Now that we can hit enter, and then you can like turn them on and off. So for example, if you click on these circles here, you can mess around with the colors, whatever, have some fun with that. But yeah, we want to find the points that the plane and the parabolic cylinder have in common. And I'm pretty sure we decided it was x was 4 minus 2 times 2t squared. I could have written that 4t squared, but whatever, minus 3t, comma, 2t squared, comma, t. And what do you know? There we go. It's pretty neat that you could see that this black curve is precisely those points that we wanted to talk about. And so having it in terms of the surfaces, that describes the curve, but it's not the way that we're able to do calculations on the curve. That if we want to do calculations, like if I wanted to find out, how long is this part of the curve, or how much work, we don't have a force acting here, but if we did, how much work is being done by the force field when a particle takes this path, we have to have the R of t equation. And so anyway, I'll write it out on the next slide. I don't want to switch back too many times. The rule of thumb is that if you can avoid taking a square root when you're messing around with these equations, you're going to want to. So something that some people would do here would be to if you let y be t, then x is going to be 4 minus 2y minus 3z. And so if y is 2z squared, sometimes people will say then that z is the square root of y over 2, so square root of t over 2, comma t, comma square root of t over 2. So it's kind of right, but sort of like what I mentioned earlier today, if you take the square root and you don't do plus minus, you're not getting the whole thing. That if z is the square root of t over 2, remember the square root only spits out the positive square root. If I wanted it to be negative, I'd have to put a negative out front here. So, I could add in another equation with a negative on these square roots to get the entire thing, but the best solution for this is going to be to do it with one equation if you can. And so the better way is to avoid taking the square root. Let z be t and y be 2t squared. That'll let z be positive or negative. Whereas if you let y be t, then z is going to, if you only take the positive square root, you're only going to get the z positive part of this. So look, you're only getting half of the curve instead of the entire curve. So let's go back, stop share, share screen. So rule of thumb, avoid square root if possible. I guess there are some complicated curves where no matter what, you're going to end up having to do some piecewise type scenario. But if you can avoid having to do piecewise, then I think you should avoid doing that. So that, you could do R of t is 4 minus 2t, and then minus or plus square root of t over 2, comma t, comma plus minus square root of t over 2. That would be okay, but you're making it unnecessarily complicated. And if you didn't do this plus minus, if you didn't do both possibilities, then you'd only be getting half of the curve. So this is okay, but more complicated. And without plus minus, it's not okay, since you're only getting half the curve, as I showed you at GeoGebra a second ago. So the rule of thumb, if you can get out of needing a square root, you should. And plus, it's lazier anyway, right? My opinion in math and in life is that the laziest correct way to do something is usually the best way. So if I already know what y is in terms of z, if I just let z be t, I don't have to I didn't do any math here, really. I mean, I guess I solved for x. That's the only thing I really did here. But that's the idea, that keep the ultimate goal in mind, that we want x, y, and z each in terms of t. And it's the kind of thing that if you know what you're doing and you've practiced this a couple times, it feels like you're not really doing much at all. But if you haven't practiced this, if you're not really comfortable with what our goal is, then these questions are a lot scarier than they should be. Okay, and then I guess the other kind of example would be to use something involving cosines and sines. So same kind of thing, find the curve of intersection of a plane and a circular cylinder. So avoid the temptation of trying to do z is plus minus square root of 9 minus x squared. I mean, if you do consider plus and minus, you can sort of make that work, but that's not the best way to do it. The best way to do it is to say that, oh, you know what? If I let x be 3 cosine t and z be 3 sine t, then I'm fine. I'll trace out the entire circle there. And yeah. So then now that I know x and z, I can get that y is 2 minus 2x minus 4z all over 3. So if I substitute in, I'll get that r of t is x, y. So plug in for x and z in terms of t, and then z. And that's it. That our goal is to get x, y, and z each in terms of t. And that'll do it. All right, so that's pretty much all the calculations from 13.1. I think on the homework, you'll get to practice some of that. And then in addition, I think there's a couple matching questions. Feel free to use GeoGebra to help you out while you're getting your intuition for these vector equations and curves that live in space. But yeah, that's pretty much it from 13.1. And so I guess now it's time to rectify the fact that you've been getting ripped off a little bit. This is a calculus class, and we have not been doing any calculus yet. And today that's going to change. So 13.2 talks about derivatives and integrals of vector functions. And so on the base level, calculus in terms of vector functions, for the most part, is really just calculus on the components. And so if we want to talk about the limit of a vector function, we're basically going to think of the limit of each component function separately. And so, the limit of r of t exists precisely when all three of those limits of the component functions, f, g, and h, exist. Same thing for continuity, that we'll call a vector function continuous when all of your component functions are continuous. Okay, and then for derivatives, we're going to define the derivative of a vector function using the same kind of difference quotient that we used for derivative of a function back in Calc 1. So we're going to define r prime of t to be the limit as h goes to 0 of r of t plus h minus r of t over h. And so that's how we define it. And in the next slide, I'll show you visually what that tells us. So looking at this difference quotient definition gives us a good idea of the geometric significance of r prime of t. But just like in Calc 1, you guys don't like to deal with the limit definition. I don't like to deal with the limit definition. We prefer to have a more efficient way of calculating derivatives. And so luckily, we do kind of what you would expect for r prime of t, that basically you just take the derivative of each component. And so, yeah, if you have r of t is fgh, r prime is f prime, g prime, h prime. So for example, for that vector equation, we just take the derivative of each component, and that's r prime of t. So nothing too complicated there. So finding the derivative, no big deal. As far as the geometric significance, let's look at this limit idea. And so if you think back to Calc 1, there was this idea of a secant line that as you take the limit, as the 2 points become 1, turns into a tangent line. So if this vector is r of t, and this is the vector r of t plus h, those are 2 points on our curve C, right? So let's call those 2 points P and Q. And so r of t plus h minus r of t is just going to be this displacement vector from P to Q. And since it's connecting 2 points on the curve, we'll call that a secant vector. Okay, and then so what happens when you divide by this number h? So h is just a scalar, otherwise you can't divide by a vector, that would be nonsense. But when you divide by h, remember scalar multiplication either stretches or compresses. So I guess the idea here is maybe h is like, I don't know, 2/3, because it looks like we've stretched PQ displacement vector by 50%. So dividing by 2/3 is the same as multiplying by 1.5. So I don't know, maybe h is 2/3 in this picture, so that when I divide by h, I get something slightly longer. And then you take the limit as this h goes to 0. As h goes to 0, that's going to send point Q towards point P. And so you're going to get all these other secant type situations. And finally, in the limit, you'll get something that's tangent to the curve. So we're going to call r of t, think about that as like the position vector of points on the curve. And then r prime we'll call the tangent vector, because the whole idea is that it's tangent to our curve. Okay, so Calc 1, what was one of the first things you did with derivatives? Well, tangent lines. So if I want to find the equation of a tangent line to a curve, if you think back to what you did in Calc 1, you know, tan line to y equals f of x at x equals a, you did y equals f of a plus f prime of a times x minus a. And so this is the number one mistake you want to make sure you don't make, is forgetting to plug in for a number. That if I left it as y equals f of a plus f prime of x times x minus a, if I leave an x there, then this is like non-linear. That if I have x appearing in f prime times this x here, that's not going to give me the equation of a line, and it turns out that it's not tangent either. So like if you forget to plug in a number to the derivative, you're 0 for 2. You're not getting a line, you're not getting something tangent. And so if you think, okay, you know, I have my curve, I want this tangent line, well, because the tangent vector is tangent to the curve, that's what we'll use as the direction vector for the tangent line. And so the whole idea is that we're drawing the tangent line at a specific point. So let's say r of t naught is the point on the curve at which we're trying to draw the tangent line. And so then r prime of t naught, not t, but of t naught, is the direction vector for the tangent line at that specific point. And then you could do parametric equations, you could do vector equation. I just wrote L of t because R of t is the name of the curve vector equation, so I just picked L for line, whatever. Okay, so example, find the tangent line to the curve R of t is t squared plus t, 2t plus 3, t cubed at the point 6, 7, 8. Okay, so we need R prime of t. So 2t plus 1, 2, 3t squared. Okay, so don't do this. L of t is 6, 7, 8 plus t times 2t plus 1, 2, 3t squared. No! That's not tangent, it turns out. You could figure it out. And not a line. Remember our line equations last week, we never had things like t squared or t cubed or anything like that. So that's no good. Like this needs to be a vector with numbers only. Okay, and then the other thing that's terrible that I've seen before is people trying to plug in 6, 7, and 8 into R prime and getting something like 13 to 192. And that's, I don't know, just as bad, maybe worse. Please don't do that. Because t is a single number, not 3 numbers together. So don't do that either. That's really bad. But if you stop to think about it for a moment, you'll be able to figure out what the only thing it would make sense to do. That if you look back at this picture, this point here, that's our point 6, 7, 8 that we're talking about. What I need to do is figure out what value of t I plug in to R to get 6, 7, 8. So like I need to figure out a value of t that makes all 3 of those true. I need that t squared plus t to equal 6. I need 2t plus 3 to be 7. And I need t cubed to be 8. And so you have to get one value of t that works for all 3. If you can, then you're done. So notice t equals 2 works for all 3 of these. But then if it turns out that you can't make all 3 of those true, then I lied to you, and that point isn't actually on the curve. Again, remember the whole idea with these vector equations from the very first slide from today, that all you're really doing is plugging in values of t to get x and y. So I need to figure out which value of t spits out 6, 7, 8, and it turns out for this, it's t equals 2. Okay, so then the correct way to do this is R prime of 2 is what? 5 to 12. And so I could write it in vector form. L of t is 6, 7, 8 plus t times 5 to 12. And what do you know? That looks like a line equation like we did. Or you could write it out with parametric equations. You could say x is 6 plus 5t, y is 7 plus 2t, and z is 8 plus 12t. But that's the idea. You need a t value to plug in. Don't do nonsense like that. Don't not plug in for t. It's really a pretty simple problem, but it always surprises me how many people make those pretty major mistakes for this. So don't fall into those traps. Okay, and then we have all kinds of derivative rules from Calc 1. And since our derivative of vector function is just defined as the derivative of the components piece by piece, all our calc derivative rules will tell us of derivative rules for this situation. So pretty much everything you hope to be true is true. So for example, the derivative of the sum is the sum of the derivatives. The derivative of a constant scalar factor times a vector function is that scalar constant factor times that vector function. And then we have three flavors of the product rule corresponding to the three multiplication-ish like operations we have for vectors. So if I have a scalar function times a vector function, that's like scalar multiplication, I get that flavor of the product rule, which if I gave you guys a few minutes to think about this, I bet most of you would guess that this is what would be the case based on what you know about Calc 1. And yeah, I can dot product two vector functions together, and I get similar kind of product rule that you would expect. I can cross two vector functions together, get this similar type of product rule as you would expect. And then finally, I could do a chain rule, which probably the chain rule you're more used to seeing outside prime of inside times inside prime. But I think we usually think of scalar multiplication as scalar times vector, but you could write it vector times scalar if you wanted to. But yeah, like we usually write 2u instead of vector u times 2, but it doesn't really matter. But if you write it in that more conventional order, you put the scalar thing first and then this here. So vector function of scalar function is derivative of the inside times the derivative of the outside of the inside. So with Calc 1, scalar functions everywhere, that's not it. We usually write it the other order. Okay, and so how are some of these useful? I think I'll show you two of them. So something we may come across, or that we will come across tomorrow, is for certain calculations, we're going to want to take a derivative of something like this, where you have some denominator that's a scalar function, and you have some vector function in the numerator, and so overall that gives you a vector function. So if I have r of t as this, and we want to find r prime of t, there's sort of two ways you could do it. One way is to do this scalar multiplication, scalar division, whatever you want to call it, right? Just remember how vector arithmetic works. That's what r of t is, 2t over 2t plus 1, 3t squared over 2t plus 1, e to the t over 2t plus 1, in which case r prime of t, you would do the quotient rule on each component. Remember the good old quotient rule, or the bad quotient rule? I don't know. I hate the quotient rule. I try to avoid doing it whenever I can. So I'm going to show you a way to get around it. But you can't just ignore it entirely, obviously. But yeah, that's one way you could do this. But the way I like to do this is to think about it as that this is 1 over 2t plus 1 times the vector 2t, 3t squared, e to the t. And realize that this is a scalar function times a vector function type situation, right? This is our scalar function f of t, and this is our vector function u of t. And so what we'll do is use the scalar function vector function product rule. So r prime of t, I get minus 1 over 2t plus 1 squared times 2 times our vector function plus scalar function times derivative of the vector function. And I prefer that a lot to doing the quotient rule 3 times. God, I can't stand to do the quotient rule once if I can sneak my way around it. But we have to respect it. And so if you have a scalar function in your denominator, like in this, you can treat it as a scalar function, vector function product rule, and take care of it like that. And it behaves just like the regular good old Calc 1 product rule. Okay, and then one other application of one of these rules, one of these product rules, is the following, that if I have a vector function whose length is constant, and I don't know why this is so small, let's zoom in a little bit. If you have a vector function whose length is constant, it turns out that its derivative has to be perpendicular to it. And okay, I think this picture should make sense, that if your curve has constant length, then it lives on a sphere, right? If the length of R of t is c, where c doesn't depend on t, then your curve lives on the sphere of radius c, centered at the origin. Because remember, the R of t, it's just position vectors of points on your curve, and position vectors always start at the origin. So if each point on my curve has a position vector that's the same length, c, that curve has to live on that sphere. And so if your curve lives on that sphere, then you think about what could be tangent to it. Well, it had to be tangent to the sphere, which is going to be perpendicular to the displacement vector from the origin. So I think this is sort of, think about a yo-yo, right? If it's at the end of its rope, or if I'm swinging something around in a circle, I'm messing around with this thing here, and suddenly it snapped at the instant when it was sort of straight up, I'd know that it would go perfectly in that direction, right? Or, you're throwing a baseball. Essentially, if you're going around like this and it breaks right here, it's going to go perpendicular like that at this right angle. Okay, but mathematically, why is that true? That's just sort of intuition. Okay. And so it's going to follow from one of our product rules from the previous slides. So recall, one of the things we talked about with dot products is that when you dot a vector with itself, that's the length of that vector squared. So if the length of r prime is c, that's the same thing as r dot r being c squared. So now let's take the derivative of both sides of this with respect to t. Well, so the whole idea is that c is just some number that doesn't depend on t. So the derivative with respect to t of c squared is going to be 0. And then the dot product rule tells us that the derivative of r dot r is r prime dot r plus r dot r prime, but then dot product is commutative, so r dot r prime and r prime dot r are the same thing. I'll just write it as r dot r prime. Well, r dot r prime, if twice that is 0, then r dot r prime is 0, which is the definition of r being perpendicular to r prime. So that's not actually, that won't be true. So I'll draw you a picture in a second. Like if let's see here. Something like that. That if your curve doesn't live on a sphere, then yeah, this angle could be whatever it wants to be. And even too, for example, most random vector functions you pick, yeah, so sorry, I always forget to do this. For those of you watching on YouTube, there's a question in chat that says, would this always be true, even if you're not trapped on a sphere? And the answer is no, so that's what I just tried to draw. But like, for example, if you take even this very first example that we did, you know, r dot r prime for this one would be what? 4e to the 4t. Oh God, I mean, it's awful. But r dot r prime isn't equal to 0, which tells you that, you know, this curve doesn't live on a sphere. So this is, maybe I'll leave this here, but r perpendicular to r discussion. Yeah, so it's special to be trapped on a sphere, which gives you this nice geometric property. Because yeah, it has to do with the fact that you're trapped on that sphere. If you're making a different shape, then who knows? All right. And so that's going to come in handy tomorrow for a couple of different, I'm trying to think. At least once tomorrow, maybe twice. This will be useful to know. All right, but that's just another, that's a neat consequence of one of these, you know, these derivative rules just sort of follow from Calc 1, but since the dot product has a geometrical significance, this dot product rule gives us this neat geometric fact for when your curve lives on a sphere. All right, and then so the very last thing to talk about today is, we talked about derivatives of vector functions. Well, we can also talk about integrals of vector functions. And just like everything else we've done today as far as calculus of vector functions, it's just defined to be component by component. So the integral of a vector, well, just make a vector out of the integrals. And so tomorrow we'll talk about position, velocity, acceleration, and things like that. You've probably done this in physics courses before. If you know the velocity of a particle, you could figure out the position and things like that. So integration of vector functions, you just do component by component. So let's say I want to find r of t. If I know that r prime of t is this, and r of 0 is that. So if you take a look in the book, I think they show you how you can take care of this using a vector constant of integration. But for me, I prefer to do everything using definite integrals if I can. So for me, I'm just going to set up a fundamental theorem of calculus that I know that the change in r between 0 and t is the integral from 0 to t of r prime, right? So we have our good old regular fundamental theorem of calculus, which f of b minus f of a is the integral from a to b of f prime. And so if I'm using t in my bounds, I shouldn't use t as the integration variable. It's not, we don't have the ability to take off points if you don't do this, but like 0 to t of r prime of t dt is bad since you're using t for two rolls. It's like the independent variable of the equation as well as the integration variable. And so you want to avoid that. So whatever, technically you should do anything other than t for your integration variable. But like I said, not a huge deal. And so yeah, let's see what that does. So r of t minus 2, 1, minus 3, I could substitute in r of 0 is 2i plus j minus 3k, is the integral from 0 to t of e to the 2u plus 7 sine u plus cosine u du. And so you just do this component by component. So what's the antiderivative of e to the 2u? Well, e to the 2u over 2. What's the antiderivative of 2u plus 7? Well, u squared plus 7u. What's the antiderivative of sine of u plus cosine of u? Well, minus cosine of u plus sine of u, evaluated between 0 and t. And so then be careful, not everything is 0 at 0. So e to the 0 is 1. So when I plug in 0 and t and subtract, I'll get e to the 2t minus 1. Then I'll get t squared plus 7t, and then, okay, that is 0 at 0. But then minus cosine t plus sine t, and then minus 1 is plus 1. So just be careful when you're plugging in. Not everything is 0 at 0. And so then I guess solving for r of t, you'll get that r of t is e to the 2t minus 1 over 2 plus 2, t squared plus 7t plus 1, and then minus cosine t plus sine t plus 1 minus 3 is minus 2. And then you can check just to make sure. I mean, as long as we didn't make a mistake, r prime of t should be what we want it to be, right? And then also you could check that r of 0 is what we want it to be, 2, 1, negative 3. So, and like I said, if you want to take a look in the textbook, I think they show you how you could do like an indefinite integral. You could do like plus c, like a vector constant of integration. And then you would use r of 0 to solve for this vector constant of integration. But I prefer to do these with definite integrals, but it is up to you. But yeah, that's some calculus, so you're getting your money's worth now. And yeah, we'll pick up there tomorrow. But any quick questions before we sign off? It depends, if I told you what r of 7 was, then I would integrate from 7 to t. Or like sometimes the question might be, find r of 2, in which case you would change that to a 2 and proceed. Yeah, so it depends on what's being asked. So yeah, the question was, is it always 0 to t? Not necessarily, but usually it starts at 0 because that's what we think of as our initial condition. Anything else? Well, I'll go ahead and stop the recording, but I'll wait for you guys to leave.